So this is the first in a series for 3.3b, solving equations, and most of these equations are going to require some factoring techniques in order to solve them. So let's take a look at this equation, and I'm going to rewrite it here. Cosine of x, sine of x, minus 2 cosine of x is equal to 0. And this says find all solutions. So this means we want all of the coterminal angles for our final answer. So that'll be the nk pi and the nk2 pi sort of business that we talked about back in 3.3a at the beginning. All right, so you want to examine what form you're given in this equation here, and you want to look for a way to factor these if you can. So this one here has a GCF of cosine of x in both of these terms here. So I can factor out the cosine of x out of both of those terms, and I'm going to put it out front. So if I factor cosine of x out of cosine of x sine of x, I'll be left with sine of x. And you can check yourself by seeing whether distributing cosine of x times sine of x gets you back your original term, and it does. All right, so now I've got minus, and I'm going to say 2 is equal to 0. Now let's check that last term. Cosine of x times minus 2 is minus 2 cosine of x. All right, so I factored it. Now, we also have learned in the past that when your factors equal to 0, those are going to give you solutions. So if I set my factors equal to 0, like this, each of these factors I'm going to set equal to 0, I can find out that if this factor is equal to 0, then 0 times whatever this happens to be, no matter what it is going to be 0. You're going to get a true solution. So if you can find out what causes this factor to be 0, you're going to have a true statement if this is 0. If you can find out the value of x that causes this factor to be 0, this will be 0 here. So no matter what this is, if this is 0, you'll have a true statement. 0 times anything is 0. So when you've factored, you've got a way to find your solutions. You set your factors equal to 0, and you find out what these values of x are that make these statements true. So this first factor, cosine of x, is equal to 0. So what angle has a cosine equal to 0? So there and there, your cosine is going to equal to 0. So this is pi over 2. And this is 3 pi over 2. And when I say the cosine is equal to 0, of course, you know this by now, your x value is 0. All right, so we've got two angles there. And then for this angle over here, if I move that 2 over to the other side, that says the sine of x is equal to 2. Well, you know, if you think about it, let's think about this. Your highest value on a sine curve is 1, and your lowest value is negative 1. So that means your sine value will never go outside of that range, negative 1 to 1. So if you get a number like 2 here that's outside of that range, you're going to say there's no solution to this equation right here because that 2 is outside of the range. Now, another way of looking at this is if you wanted to solve for this x here and you said the inverse sine of the sine of x, so that would cross that out and give you x is equal to the inverse sine of 2, and you tried to type that into your calculator, inverse sine of 2, you would get a domain error. All right, it would say undefined. And you would stop to think, okay, what's going on here? And then you'll have to remember that 2 is outside of the range of what your sign values can be, which is -1 to 1. Now, since we're asked to find all solutions, we've got to think about coterminal angles here. So we can start out with our lowest angle. So x is equal to pi over 2. And when we can think about a pattern here. So if I go plus pi, I'll hit 3 pi over 2. So I can call this pi over 2 plus pi. And then if I go around another time over here, so this is 1/2, 2/2, 3/2, 4/2, 5/2, I'll get pi over 2 plus 2 pi. That's 4/2. And then you'll get pi over 2 plus 3 pi. And then it'll keep going on and on and on till infinity. And so you'll have infinitely many angles that have a cosine of 0. So we can write that as x is equal to pi over 2 plus multiples of pi. And that's how we can write our solution, where k is any integer, meaning it could be also a negative number. Integers are -3, -2, -1, 0, 1, 2, 3 in both directions. That's what we mean by an integer. So this is your solution. Okay, here's another problem. This one says solve for x. And let me just add that we're on the interval 0 to 2 pi this time, as opposed to last time where we said find all solutions. All right? So this is just on the interval 0 to 2 pi. So we're not looking for the coterminal angles like we did last time. So let's see if we can factor this. So I'm going to write it out. All right. Now let me just remind you as an aside, if you saw a problem that looked like this, where the only difference is there aren't any signs, okay, instead of sine x, we're using just plain x, that's a quadratic. Okay, one of the techniques we know for solving quadratics is you could factor it and set those factors equal to 0 and find the x's that cause those factors to be equal to 0. So we're going to do it the same way. All right, so I've got a leading coefficient of 2 here. So let's figure out how to factor this thing. So 2 times 1 is 2. So I need the ways to multiply to give 2. 1 times 2 is the only way to get 2. All right, so I need to multiply to give 2. Whoops. Multiply to give 2 and add to give positive 3. So this middle number here will tell you your signs, what your signs are over on the factors. So I'm going to need 2 positive signs, positive 1, positive 2, to add up to give me 3. So I'm just doing regular old quadratic factoring here. So since I have a leading coefficient of 2, I have to factor by parts. So I'm going to put, instead of 3 sine x in the middle, I'm going to break that term up into what I have here, 1 sine of x plus 2 sine of x, which equals 3 sine of x. All right, let me put the 2 first and the 1 second. So that's my middle term. And then I have this plus 1 equals 0. All right? So far, I haven't done anything that isn't the same as what you would do to solve for these factors here. All right, so now if I break it down in the middle, before that plus, I can factor by parts. So I'm going to factor the GCF out of the first two terms. So that would be 2 sine of x plus 1. All right, so then bring this plus down. So I have a GCF of 1 out of the next two terms. Right, this should be the same as this if you factored correctly. And this sign here is always this sign here. So you want to check and see whether you distribute out correctly. 2 sine of x times sine x, yes. 2 sine of x times 1, yes. 1 times sine of x, yes. 1 times 1, yes. Okay, so I'm factored correctly. Now my final step, sine of x plus 1 times 2 sine of x plus 1. Right, and if you had any doubt in your mind as to whether this was equivalent to this, you could double distribute and combine like terms and prove it to yourself that this is equivalent to this. In fact, this, and this are all equivalent. All right, so now let's go ahead and set each of those factors equal to 0. Scoot it up a little. So sine of x plus 1 is equal to 0. 2 sine of x plus 1 is equal to 0. Remember, if you know factors, you know solutions. So sine of x is equal to negative 1, and 2 sine of x is equal to negative 1, or sine of x is equal to negative 1/2. All right, so looking over to the unit circle now, sine of x is equal to negative 1 at 3 pi over 2, and sine of x is equal to negative 1/2 at 7 pi over 6 and 11 pi over 6. So I'm going to have 3 solutions within the interval 0 to 2 pi, 1 revolution. I'll have, let's just list them, 7 pi over 6, 3 pi over 2, and 11 pi over 6. So just to review what we did, we look at our original statement. Here, we say, well, I could factor that. I could factor that like a quadratic. So I find the factored form. If you know factors, you know solutions. You set your factors equal to 0, and you solve for x in both of these cases. So if I look over here in my unit circle, I can find the angles that give you a sine equal to negative 1, and there's 2 that give you a sine equal to negative 1/2, and I just list those angles. All right, this problem says, given cosine of 2x is equal to the cosine of x, solve on the interval 0 to 2 pi. All right, so we're going to move everything over to one side and see if we can factor this first. Okay, so I'm looking at this thing and thinking, well, there's a problem here because I've got a 2 in front of this x, but I don't have a 2 in front of this x, so they basically aren't the cosine of the same angle. All right, so I can't subtract these two because they're not like terms. So what can I do? Well, sometimes what happens is you need to look at your identity paper and find a substitution for one of these terms. For instance, the cosine of 2x has an identity on your identity paper. Now, I noticed that this problem is in 3.3b. It's a little bit premature because we haven't actually done too much with these identities yet. So, but if you look on your identity paper, you can find that the cosine of 2x is equal to, this is an identity. So this problem probably should have waited until our multiple angle. Okay, so let's just write it out. The cosine of 2x is equal to 2 times the cosine squared of x minus 1. So sometimes you hit an impasse with these kind of trig functions until you figure out a substitution that you can make using an identity which allows it to become factorable or some other breakthrough like that. Mostly you're looking for ways to get them to be factorable so that you can then set the factors equal to 0. So if I replace cosine of 2x with 2 cosine squared of x minus 1, and then I have minus cosine of x is equal to 0, I can rearrange that a little bit to make it look like a quadratic setup, like that. All right, so then I can try to factor this as a quadratic. So what I'm looking for, 2 times negative 1 is negative 2. Ways to multiply to get 2, 1 times 2. All right, and that's a negative 2, so I need one negative. So if I need to add to give negative 1, that means my negative is going to have to go on the 2. So replacing the middle term with these two terms, negative 2 cosine of x plus 1 cosine of x minus 1 equals 0. So now I can factor by parts. So I'm going to cut it down the middle here. So I'm going to factor out a GCF out of those two terms, bring down my plus, factor out a 1 out of these two terms. These two should be equal, these two factors here, if you've done it correctly. All right. So now my final factored form is cosine of x minus 1 times 2 cosine of x plus 1 equals 0. So now we're able to do this. If you have factors, you have solutions. Set your factors equal to 0. All right, so that means the cosine of x is equal to 1, or the cosine of x is equal to negative 1 divided by 2. So let's see if we can figure out where that happens. So the cosine of x is equal to 1 here at 0 radians, and the cosine of x is equal to negative 1/2 here and also here at pi over 3 radians and 4 pi over 3 radians. So my solutions are x is equal to 0 radians, pi over 3 radians, and 4 pi over 3 radians within the interval 0 to 2 pi, which is 1 revolution around the circle. So to recap, if you've got a problem to solve and it's not immediately evident how it's going to happen, you want to try to see if you can get it into a form that's factorable. Sometimes you need to make a substitution using an identity. All right, so this one was a little bit more than you guys have been exposed to now, so it probably should have been in another section, but I noticed it was in this section. All right, so here's your substitution. Once you make that substitution, it is factorable like a quadratic. Once you have your factors, you set them equal to 0 and solve for the values of x, the angles that make these two statements true. All right, so we found 3 angles that make these factors true statements. So there's a mistake I found here. So this should have said 2 pi over 3, 2 pi over 3. There we go. All right, so here's another problem. Solve for x, and let me add on the interval 0 to 2 pi. Okay, well, let me take that back. On this one, we're going to say find all solutions. So when it says find all solutions, we're talking about the nk and the nk 2 pi stuff. We got to figure out all the coterminal angles. So let's try one like this. All right, so if I rewrite sine squared of x plus 10 times the cosine of x, I'm going to bring the 10 over on this side and then examine it to see whether it's factorable. Right, I see a problem here. Sine and cosine are mixed together in this problem. We want to either have it all in terms of cosine or all in terms of sine in order to be able to factor it. All right, so I do know right now that there is something that we can do. So I know that the sine squared of x plus the cosine squared of x equals 1 is an identity that we've used plenty before. All right, so if I want to find a replacement for sine squared of x, that means I've got to move this over to the other side. Let's just scoot this over so that I can cancel it out. So I can figure out just sine squared of x, 1 minus cosine squared of x. All right, so wherever I have a sine squared of x, it can be replaced with 1 minus the cosine squared of x. So let's do that. So I've got 1 minus the cosine squared of x plus 10 times the cosine of x minus 10 is equal to 0. So now you can see I'm going to be able to get this into a quadratic looking format. Squared here, first order term here, and then constant here. So let's combine this 1 and the negative 10. So I'll have negative cosine squared of x plus 10 cosine of x minus 9 is equal to 0. All right, I don't want to try to factor with a leading negative, so I want to divide by negative on every term, which changes the signs of all the terms, like that. So now let's check and see if we can factor this. So this is a leading 1 here. 1 times 9 is 9. Ways to multiply to give 9. 1 times 9 and 3 times 3. So we need a positive 9 multiplying and a negative 10 adding. So if we put 2 negatives on here, we should be able to do it. Now notice that your leading coefficient is 1. If your leading coefficient is 1, you automatically know that your factors don't need to have a coefficient in front of the cosine. So you can just plop these 2 numbers right into the factors. When that happens, it's a little quicker. All right? That's only if this leading coefficient is 1. Can you do this? All right? So now we have factors. Once you have factors, you have solutions. So cosine of x minus 9 is equal to 0. Cosine of x minus 1 is equal to 0. Cosine of x is equal to 9. Or cosine of x is equal to 1. Well, you can't be 9 because remember it has to be between negative 1 and 1 if you're a sine or a cosine. So we're not going to get a solution from that side of it there. But over here, we can say the cosine of x is equal to 1 when you're at 0 radians. All right, so if we're asked to find all solutions, we're going to say x is equal to 0 plus all coterminal angles of 0 degrees. So those are multiples of 2 pi, and that's because you have to go 2 pi, 2 pi, 2 pi, or the other way, 2 pi, 2 pi, 2 pi, in order to hit back on that dot again. So all of your solutions, if we write it out, are going to be x is equal to 2 pi times k, where k is any integer. All right, so this will be your solution. All right, let's do one more of these. All right, so here we'll say on the interval 0 to 2 pi. All right, so we're not looking for the nk pi or the n pi stuff this time. All right, that's messy. Okay, so I rewrote my problem. Now I'm going to examine it to see if I can factor it. Well, right off the bat, I can see I have a mixture of sines and cosines right here. All right, so we're going to have to do a substitution somewhere. And if you see a sine squared, you're going to remind yourself of our identity that says sine squared of x plus the cosine squared of x is equal to 1. So if we want a substitution for the sine squared of x, that means we want to move the cosine squared of x over to the other side to get an equivalency. So that means wherever I've got the sine squared of x, I can replace it with 1 minus the cosine squared of x, like that. Now let's organize it a little. So I want my quadratic set up. So I want my squared term first, then my first order term second, and then I want to combine 1 plus 6. And then I want to divide through by a negative so that I'm not factoring with the leading negative, because those are usually going to end up confusing. All right, so divide through by a negative. So now I've got a 1 as my leading coefficient, and I've got a 7. 1 times negative 7 is my multiply. Only one way to multiply to give 7. They have to add up to give you negative 6. I need 1 negative. So 1 negative on the 7. So putting, well, let's look. I have a leading coefficient of 1. So I can skip the factoring by parts step if you have a leading coefficient of 1. So I know that I'm not going to have a coefficient on these cosine of x terms here if you have a leading coefficient of 1. So I've got a positive 1 and a minus 7. All right, so if you have factors, you have solutions. So I've got cosine of x is equal to negative 1. Oops, I skipped a step. Cosine of x plus 1 is equal to 0. Cosine of x minus 7 is equal to 0. Cosine of x is equal to negative 1. Cosine of x is equal to 7. All right, so cosine of x is equal to 7 is out of the range, negative 1 to 1, so this is no solution. All right, on that branch. Over here, though, cosine of x is equal to negative 1 at pi, right? So x is equal to pi. Let's write it over here. X is equal to pi is your solution. All right. So if I would have asked for all solutions, you would have written x is equal to pi plus all multiples of 2 pi. All right. So regardless, by now you're probably starting to get the hang of it. So this one is if you're asked on the interval 0 to 2 pi. This one if you're asked for all solutions.